We use mental maps to navigate reality, and those maps in our minds are made of stories. Today I want to talk about this study, Serotonin release in the Habenula during emotional contagion promotes resilience. And the TLDR is the researchers put a bunch of mice through struggle while others watched. And the mice that watched the struggle were later able to go through it themselves and had fewer depression symptoms afterward. And if that's all you wanted to know, thanks for watching. Hit the like on your way out. Otherwise, let's go a little deeper. This is a map of the default mode network in our brains. This runs probably about half the time when we're awake. And the time when it's most active is when we're not doing anything, when we're just kind of sitting there chilling, relaxing. So when you're daydreaming or thinking about the future or reliving past experiences, this is what's running. On the left-hand side here, it also contains a lot of the structures that are centers for language in our brain. The default mode network is mainly focused on the self. In fact, it's almost entirely focused on the self. So the things you say to yourself when you're just sitting there are coming from this. And one part I want to real quick point out is it includes this, the medial prefrontal cortex. And that's actually very important because that basically contains most of the executive function in the brain. Here's another image of it. All these little lines and filaments show how these parts are functionally connected. That medial prefrontal cortex is fairly new, but the part they looked at in this study, the Habenula, is actually very, very old. And specifically, they looked at what was going on in this little portion, the Lateral Habenula. And for a long time, it was thought that this part of the brain was just kind of a brake, acted as a set of brakes on the reward pathways in our brains. And those reward pathways are what you're making use of when you're pursuing food or mating or, in the case of addicts, drug-seeking behavior. And it's actually turned out that there's more to it because, of course, there's more to it. It actually kind of acts as a modulator. So when it's functioning properly, it helps us to discern between which rewards are more desirable and which are less desirable. In essence, it helps us to prioritize our activities. What this image shows is a couple of mice, obviously, but this is supposed to be a normal mouse brain, and this is the brain of a depressed mouse. And these bars here are activity in that lateral habenula. And what you'll notice is in the depressed mouse, there is more activity in that particular part of the brain, while in the normal mouse, there's less. And another thing to notice is the normal mouse and the depressed mouse are the same mouse. They subjected it to chronic stress, and that wound up producing these depression-like symptoms. Like I mentioned, this is an ancient part of the brain. It's been around for probably a couple billion years. Here it is in zebrafish. It takes in information from the thinking part of the zebrafish's brain and then outputs to the reward centers. You can see in the rodent, it's actually much, much more complicated, but it's basically the same principle. And down here, this is the rhesus monkey. And up here, I'm sure you recognize this as a human brain. And it takes in information from, among other things, the medial prefrontal cortex. And that's basically the only true thought part, or at least what we would recognize as thought, that comes into there. So I looked up all the different input pieces, the parts in green from this image. And if you'll look at it, you'll notice that very, very little of it is sensations that come from outside the body. Most of these are internal sensations. The only exceptions, and I should say this is just stuff that's been found so far, but the only exceptions are temperature sensing and smell. Now, the output from this part of the brain actually goes to these little pieces that either produce dopamine directly or they send signals to other parts that then produce dopamine. So when that piece of the brain becomes hyperactive, it actually slows down the reward-driven activity. So let's get into this study and what they did with the mice. First, what they did, they put one up on a higher level and one on a lower level, and then they shocked this one on the lower level once per minute for 19 minutes. And those were basically just foot shocks that caused pain but didn't actually harm the mouse, while the other had these holes so it could watch what was going on. Well, when a mouse is getting shocked like that, it starts pausing and looking around and trying to figure out when the next one is coming or if another one is coming. And they found that the bystander mice would perceive that and begin to replicate the behavior. And that's what they called negative emotional contagion. They assume the bystander mouse is having kind of similar emotional reactions that the demonstrator mouse is having. Then the next day, they took some of those bystander mice that had watched this go on and subjected half of them to the same shocks. Then they tested them for depression and despair by putting them through the tail suspension test. Basically, the way the tail suspension test works is they tape their tails to a hook and they leave the mice there for 6 minutes. In general, most mice will try to find a way out of it for about 2 minutes. Now, some are so athletic that they basically climb up their tail and unhook it, and they get out of the test that way. But most of them aren't able to do that, so they hang there for 2 minutes trying to get out of it, and then some just stop while others keep trying. The more time the mouse spends just hanging there versus trying to escape is considered an indicator of depression and despair. So right here, this shows the immobility time. These were the control group of mice that didn't get any shocks. This was a group that got foot shocks but wasn't able to be bystander first, and you can see they have much more time being immobile. These were the mice that were bystanders, but they didn't get any shocks at all. And you can see they performed just as well as the control group. This group was bystanders who observed others getting shocked and then got shocked themselves. And they performed basically just as well. In order to try to explain these outcomes, they looked at serotonin in the habenula. Now, the serotonin that's in that organ isn't produced there. It's produced right here in this part called the raphe. And what they did, they ran fiber optic tubing into their skulls, all the way down to those parts. They also inserted a viral vector that contained the instructions to produce this protein, GRAB. And GRAB basically would attach onto serotonin and create kind of this fluorescent effect. And what they found was that serotonin levels were actually higher in the group that had been bystanders first than it was in the control group. So that greater presence of serotonin in the lateral habenula was associated with fewer depressive symptoms after going through pretty severe adversity. Then they did some photobiomodulation therapy on these mice. Basically, they put another fiber optic cable into the raphe in their brain, the part that was producing serotonin, and they had that fiber optic cable hooked up to a red light. And that red light is this 638 nanometer wavelength. Anyway, by shining that light in that part of the brain, they were able to get it to produce more serotonin. In this study, they referred to serotonin as 5-HT, so wherever you see that, just think serotonin. And where there were higher serotonin levels, there was less activity in that lateral habenula. They also tested this particular SSRI, this antidepressant, to see if it had a similar effect. And it did. It had a similar effect of reducing the amount of bursting, but it was basically the same outcome as those that just watched the other one go through it first. This study shows a mechanism. by which seeing other people's stories of resilience helps us develop our own.